Let's dive deeper into this digital thread. The connected bidirectional digital thread supporting our digital twins is a key piece to this full lifecycle story. As we look at this diagram, I'm going to walk you through how we use digital twins and the terminology we use. So I think that's important. There are many definitions out there and many opinions and thoughts about digital twins. I'm not trying to say one is right and the others are wrong. What I do feel is important, though, is sharing and level setting by providing the terminology that I am using, that we are using, so that when we have a discussion, when we talk, when we share information, that we can understand. You can understand where I'm coming from. So, at Northrop Grumman, we align with the Digital Twin Consortium's definition. So, digital twin is a virtual representation of real-world entities and processes synchronized at a specified frequency and fidelity. Of course, in aerospace and defense land, our specified frequency might be a little wider than some others. Sometimes joke, right? It's a little different than our washers and dryers that may be connected right to the internet. We might need to do some extra work to get the data back from our systems. So let's, again, dive in here. So this all begins back with mission engineering and mission simulation and analysis. Very beginning, down around point 1 there, bubble 1. So what are we doing there? We are working with our customer to model the mission long before we're on contract to build. We're working to understand the problem space, working with our customer, ensuring that we understand the solution, so that then we can continue on leveraging digital twins at that point. Even move through that requirements, again, mission engineering, functional system modeling, analysis of alternatives, continues on through design. During that time, we're building and evolving the prototype digital twin prototype, the as designed digital twin, leveraging the best design information that we have at a given time. The data we're using may be synthetic, or maybe it's off of something similar that we're able to leverage. But we're using that to evolve and optimize our design, make it the best that it can be. The story continues on through simulation, test and verification, into manufacturing, intelligent manufacturing, production, automation. At that point, we're talking about the as-built digital twin. So now we may have a physical thing in our facility, in our factory, that we can, again, begin learning from. We can pull metrics from. We can inform our model, inform our digital twin, which has now progressed then from digital twin prototype to being a digital twin synchronized with the real. Once again, the story does not end there. It continues on. So we continue moving through, we deploy, we put that system into operation, sustainment. And once again, we're talking about now what I would refer to as the digital twin aggregate, digital twin instance. Digital twin aggregate maybe being related to a lot production run specific to that time frame of those systems as they were built. Digital twin instance may be specific to a tail number, a serial number. Once those products, those platforms are employed in the field, they are out in the field, they're being maintained and sustained, things change. Our military makes the updates they need to do, makes repairs, maybe due to the environment, there's some changes in how it operates. We bring that back specific to that digital twin instance. Leveraging this engineering rigor across the full thread is what makes it valuable. This is a bidirectional thread to support informing the digital twin with data from the physical, and again, thus maturing that digital twin, empowering it to solve the challenges of tomorrow. The forming of this bidirectional thread enables data-driven insights like never before, reducing risk through enhanced visibility, bolstering the quality of our products and improving manufacturing operations. This has enabled our program performance so we can continue to deliver with speed, quality, and efficiency. So let's dive a little bit deeper into this digital thread, digital twin, really digital engineering. It's all about optimizing our product design, getting more and more confident before I order my first bolt, let alone turn the bolt, order the bolt. Before we even bend metal, we've already modeled it. This leads to increased customer confidence and decreased risk. We're ultimately decreasing uncertainty by leveraging data from that digital thread and employing it to power our digital twins. Connecting the digital thread from the capture phase through requirements, model-based design through model-based manufacturing, test and integration, and all the way to model-based simulation is critical to the employment of digital twins, as the maturity of the twin should increase as that product lifecycle progresses. As the world changes, sadly, we're hearing about scary events in other parts of the world, all over the world. At any time, our customer could call on us to understand how to leverage their platforms, their products effectively. Could talk through a hypothetical scenario. There's a new threat. Customer doesn't know quite yet how it will respond. We can rely on our digital twins, our digital twin instances, to confidently answer the call and drive mission success. So let's think about that. We go back to our mission engineering, mission simulation and analysis. So all the way back to the beginning now, a new problem set. Work on modeling, simulating that arena, that problem space. Help our customer to understand maybe how they could employ these and how effective something might be, so that we can confidently answer their call so that they can make the decisions they need to make, maybe employ a specific serial number, tail number, given where it happens to be in the world, and know how effective it will be. So we can rely on our digital twins, digital twin instances to confidently answer that call and drive mission success.